All right, welcome to lecture 16, where we'll be discussing weak convergence, also known as convergence in distribution. Let's begin with the formal definition of convergence in distribution. A random sequence X which maps our sample space omega to the space of real valued sequences R to the n, all defined on a probability space omega script f. P is said to converge in distribution to a random variable x infinity, which maps a possibly different sample space omega prime to R and is defined on a probability space omega prime script f prime p prime if the limit as n tends to infinity of the cumulative distribution function f sub x sub n of x equals f sub x infinity of x at all points x where f sub x infinity is continuous. This type of convergence in distribution is typically denoted by writing the limit as n approaches infinity of x sub n equals x infinity in distribution. Now let's consider random sequence X mapping from omega to R to the n, defined on a probability space omega, script f, p, and a random variable x infinity mapping from omega prime to R, defined on another probability space omega prime, script f prime, p prime. Then the following statements are equivalent. First, the limit as n approaches infinity of x sub n equals x infinity in distribution. Second, the limit as n approaches infinity of the expected value of g of x sub n equals the expected value of g of x infinity, and this must hold for any bounded continuous Borel measurable function g that maps from the real numbers to the real numbers. This is often called the portmanteau theorem or part of it. And third, the characteristic functions converge pointwise. That is, the limit as n approaches infinity of phi sub x sub n of u equals phi sub x infinity of u for each real number u. This is a very powerful equivalence, often known as Levy's continuity theorem. For the proof outline, let x be our sequence of random variables and x infinity be the limiting random variable. We will sketch the implications. A implies B, B implies C, and finally C implies A. To show that convergence in distribution, which is statement A, implies statement B. Regarding the convergence of expectations of bounded continuous functions, we would typically apply a result like the Helibret theorem. This states that if the distribution functions f sub x sub n converge weakly to f sub x infinity, then the integral of g of x with respect to df sub x sub n of x converges to the integral of g of x with respect to df sub x infinity of x for bounded continuous g. To show that statement B implies statement C, that is, convergence of expectations of bounded continuous functions implies pointwise convergence of characteristic functions, we simply choose our bounded continuous function g of x to be e to the power j ux, or more rigorously we can consider its real and imaginary parts, cosine of ux and sine of ux, both of which are indeed bounded and continuous. The result for the characteristic function then follows directly. The implication that statement C implies statement A, meaning that pointwise convergence of characteristic functions implies convergence in distribution, is the most substantial part of these equivalences and is often referred to as Levy's continuity theorem or the convergence theorem for characteristic functions. The proof is quite technical and is generally omitted in an overview like this, but is a cornerstone of advanced probability. Let's consider an example that illustrates convergence in distribution, but not necessarily convergence in probability. Imagine a sequence of non-degenerate continuous IID random variables, which we'll call X, mapping omega to R to the N, and let Y be an independent random variable, mapping omega prime to R such that all these random variables, the X sub N's and Y, share a common distribution function f sub y. In this setup, the distribution function f sub x sub n is equal to f sub y for all natural numbers n. Consequently, the limit as n approaches infinity of f sub x sub n of x is simply f sub y of x for all x. Therefore, x sub n converges to y in distribution quite trivially. Now, let's make this more concrete. If this common distribution f sub y is a zero mean Gaussian distribution with variance sigma squared, then the difference x sub n minus y, since x sub n and y are independent Gaussians, will also be a zero mean Gaussian, but with the variance of sigma squared plus sigma squared, which is 2 sigma squared. Therefore, for any epsilon chosen to be less than sigma times the square root of pi, and for all n, the probability that the absolute difference x sub n minus y is less than or equal to epsilon can be found by integrating the Gaussian density with variance 2 sigma squared from minus epsilon to epsilon. This integral 1 over the square root of 4 pi sigma squared times the integral from minus epsilon to epsilon of e to the minus z squared over 4 sigma squared dz can be bounded above. For small epsilon, this probability is approximately 2 epsilon divided by the square root of 4 pi sigma squared, which simplifies to epsilon divided by sigma times the square root of pi. If epsilon is small enough, this value is strictly less than 1. It follows that the probability that the absolute difference x sub n minus y is greater than epsilon is bounded below by 1 minus epsilon over sigma square root of pi, which is a positive constant that does not go to 0. Hence, x sub n does not converge to y in probability, even though it converges in distribution. An important lemma states that convergence in probability implies convergence in distribution. So if we have a sequence of random variables x and a random variable x infinity, all defined on the same probability space omega script f p, such that x sub n converges to x infinity in probability, then it must also be true that x sub n converges to x infinity in distribution. To prove this, our goal is to show that for all continuity points x of the distribution function f sub x infinity, the limit as n tends to infinity of f sub x sub n of x equals f sub x infinity of x. Let's fix an arbitrary epsilon greater than 0 Since x is a continuity point of the non-decreasing function f sub x infinity, we can find a delta greater than 0 such that f sub x infinity evaluated at x plus delta minus f sub x infinity evaluated at x minus delta is less than our chosen epsilon. Therefore, it suffices to demonstrate the following sandwich inequality. F sub x infinity of x minus delta is less than or equal to the limit inferior as n goes to infinity of f sub x sub n of x, which in turn is less than or equal to the limit superior as n goes to infinity of f sub x sub n of x, which itself is less than or equal to f sub x infinity of x plus delta. For our chosen delta greater than 0, let's consider the event a sub n of delta defined as the set of omegas where the absolute difference between x sub n of omega and x infinity of omega is greater than delta. This is equivalent to the event that x sub n does not fall within the interval from x infinity minus delta to x infinity plus delta. Also, let a sub x sub n of x denote the event that x sub n is less than or equal to x, and a sub x infinity of x denote the event that x infinity is less than or equal to x. We can then establish some useful set relations. For instance, the event x sub n is less than or equal to x is related to x infinity is less than or equal to x plus delta, and the event a sub n of delta. Specifically, f sub x sub n of x is p of x n lesser than or equal to x. We can show that f sub x n of x is less than or equal to f sub x infinity of x plus delta plus p of a n of delta. Similarly, f sub x sub n of x is greater than or equal to f sub x infinity of x minus delta minus p of a n of delta. These inequalities arise from considering the implications of xn being close to x infinity. Combining this, we get f sub x infinity of x minus delta minus p of a sub n of delta is less than or equal to f sub x sub n of x, which is less than or equal to f sub x infinity of x plus delta plus p of a sub n of delta. Now, because x sub n converges to x infinity in probability, we know that the limit as n approaches infinity of the probability of a sub n of delta is 0. Taking the limit inferior and limit superior as n tends to infinity, our derived inequality, and using the fact that p of a n of delta vanishes, we are left with f sub x infinity of x minus delta is less than or equal to lim inf f sub x n of x, and lim sup f sub x n of x is less than or equal to f sub x infinity of x plus delta. Since epsilon and thus potentially delta can be made arbitrarily small because x is a continuity point, the result follows. Now let's turn to one of the most celebrated results in all of probability theory, the central limit theorem. Consider an IID independent and identically distributed random sequence X defined on our probability space, where the expected value of each X sub n is mu, and the variance of each X sub n is sigma squared for all n. We define the n sum S sub n as the sum from I equals 1 to n of X sub I. We also consider a standard normal random variable, let's call it y, which has the familiar probability density function f sub y of y equals 1 over the square root of 2 pi times e to the power of minus y squared over 2 for all real y. The central limit theorem then states that the limit as n approaches infinity of this standardized sum, that's S sub n minus n mu, all divided by sigma times the square root of n converges in distribution to this standard normal random variable y. The classical proof of the central limit theorem relies heavily on the properties of characteristic functions, particularly Levy's continuity theorem. Let's define a new sequence of random variables z sub I as x sub I minus mu, all divided by sigma. These z sub I are IID random variables with a mean of 0 and a variance of 1. Then our shifted and scaled n sum S sub n minus n mu over sigma square root n can be rewritten as 1 over the square root of n times the sum from I equals 1 to n of z sub I. We will use the third equivalence condition for convergence in distribution that we discussed earlier, namely the pointwise convergence of characteristic functions, to show that the characteristic function of our normalized sum converges to the characteristic function of the standard normal distribution. Let phi sub n of u denote the characteristic function of the normalized sum S sub n minus n mu over sigma square root n. Let phi sub z sub I of u be the characteristic function of z sub I, and phi sub y of u be the characteristic function of the standard normal y. We know or can readily compute that the characteristic function of a standard normal random variable y, phi sub y of u, is e to the power of minus u squared over 2. This derivation usually involves integrating e to the juy against the standard normal density, often by completing the square in the exponent or using contour integration. Since the random sequence Z consists of IID random variables with zero mean and unit variance, it follows from the properties of characteristic functions that the first derivative of the characteristic function of Z1 evaluated at 0, which is j times the expected value of Z1 is 0. The second derivative of phi sub Z1 of u evaluated at 0 is j squared times the expected value of Z1 squared, which is the variance 1, 1. So this second derivative is minus 1. Now we use the Taylor expansion for the characteristic function of Z1 around the point 0. Phi sub Z1 of t is approximately 1 plus the first derivative at 0 times t plus the second derivative at 0 times t squared over 2 plus higher order terms that are little o of t squared. Since the first derivative at 0 is 0 and the second derivative at 0 is minus 1, this expansion simplifies to 1 minus t squared over 2 plus little o of t squared. the characteristic function phi sub n of u for our normalized sum benefits from the independence of the z sub i's. It's the product of n identical characteristic functions, each corresponding to z sub I over square root of n. So phi sub n of u is the characteristic function of z1 evaluated at u over a square root of n, all raised to the power of n. Substituting our Taylor expansion with t equal to u over square root of n, this becomes approximately 1 minus u squared over 2n plus little o of u squared over n, all raised to the power n for any fixed real number u. As n tends to infinity, this expression is of the well-known form 1 plus x over n to the power n, which converges to e to the x. In our case, x is minus u squared over 2. So the limit is e to the power of minus u squared over 2. This is precisely the characteristic function of the standard normal distribution, thus completing the sketch of the proof of the central limit theorem. Let's now shift our focus to the strong law of large numbers. For a random sequence x defined on our probability space, where the mean E absolute xn is bounded and finite for all n, we define the n sum S sub n as the sum from I equals 1 to n of x sub I, and the empirical n mean as sub n divided by n for each n, for each natural number n, and for a given positive epsilon, we define an event E sub n as the set of omegas in our sample space where the absolute difference between S sub n and its expectation Es sub n is greater than n times epsilon. One version of the strong law is the L4 strong law of large numbers. Let x be a sequence of independent random variables defined on our probability space with a bounded mean Exn for each n. Crucially, we also require a uniformly bounded fourth central moment, that is the supremum over n of the expected value of xn minus Exn raised to the fourth power is less than or equal to some finite constant b. The theorem then states that under these conditions, the empirical n mean S sub n over n converges almost surely to the limit as n approaches infinity of Es sub n over n. If the x sub n are identically distributed with mean mu, this limit is simply mu. For the proof, a key step is to evaluate the fourth moment of the sum of centered random variables. Recall that the expected value of Sn minus Sn to the fourth power, which is the expected value of the sum from I equals 1 to n of x I minus Ex I all raised to the fourth power, expands due to independence. The terms in this expansion consist of the sum of the individual fourth moments, that is, sum from I equals 1 to n of expectation of x I minus expectation of x to the fourth, plus terms involving products of second moments, specifically 3 times the sum over I from 1 to n and sum over j not equal to I of expectation of x I minus expectation of xi squared times expectation of xj minus expectation of xj squared. We should also recall that if the fourth moment is uniformly bounded, then the second moment, the variance is also uniformly bounded. So the supremum over E of the expected value of x, I minus EXI squared is less than or equal to some finite constant C. Therefore, applying Markov's inequality to the event E sub n, the probability of E sub n is less than or equal to the expected value of Sn minus Esn to the fourth divided by n to the fourth times epsilon to the fourth. Using our expansion for the fourth moment of the sum and the uniform bounds B and C, this probability is bounded above by nb plus 3n into n minus 1 into c squared, all divided by n to the fourth epsilon to the fourth. This expression is roughly of the order 1 over n squared. Consequently, the sum over all n of the probability of E sub n is finite. By the first Borel-Cantelli lemma, this implies that the probability that E sub n occurs infinitely often is 0. Equivalently, the probability that the complement of sub n occurs for all but finitely many n is 1. Since our choice of epsilon was arbitrary, this establishes the almost sure convergence. Next, we have an L2 strong law of large numbers. Let X be a sequence of pairwise uncorrelated random variables defined on our probability space with a bounded mean Exn for all n. Additionally, we require a uniformly bounded variance, meaning the supremum over n of the variance of xn is less than or equal to some finite constant b. Under these conditions, the theorem states that the empirical n mean Sn over n converges almost surely to the limit of Esn over n as n approaches infinity. The proof technique for this L2 version often involves considering subsequences. For instance, along n squared. For each n, we can define an event f sub n related to the deviation of s sub n squared from its mean, specifically E sub n squared, using our previous definition of En. We also define another event G sub n, which captures the maximum deviation of partial sums sk minus sn squared from their respective means over the block of indices k ranging from n squared to n plus 1 squared minus 1. More precisely, G sub n is the event that the maximum over k from n squared up to n plus 1 squared minus 1 of the absolute value of the sum from I equals n squared to k of xi minus exi is greater than n squared times epsilon. This G sub n can be expressed as a union of individual deviation events. Using Markov's inequality or Chebyshev's for Fn, which is related to En and L2, and the union bound for Gn, possibly combined with a maximal inequality like Kolmogorov's, though simpler bounds can be derived, we can bound their probabilities. The probability of f sub n can be shown to be less than or equal to b divided by n squared, epsilon squared, assuming the sum of variances for s NR2 is NR2B. The probability of G sub n can also be shown to be of the order 1 over n squared. For example, bounded by something like 2n plus 1 squared B divided by n to the 4th epsilon squared.
Since both P of Fn and P of Gn are of order 1 over n squared, their sums over all n are finite. By the Borel-Cantelli lemma, this implies that with probability 1, only finitely many of the Fn and Gn events occur. This directly leads to the almost sure convergence to 0 of S sub n squared minus Esn squared, all divided by n squared. It also implies that the maximum deviation term within the blocks when normalized by n squared goes to 0 almost surely. The final result for S k over k for any k, not just n squared, then follows by a standard argument. Any k lies between some n squared and n plus 1 squared. We can then bound the deviation of sk over k by terms involving the deviations at the n squared point and the maximum deviation within the block from n squared to k. Since both of these components go to 0 almost surely when appropriately normalized by k or n squared, this establishes the almost sure convergence for the entire sequence.
Finally, let's mention Kolmogorov's strong law of large numbers, often referred to as the L1 strong law. This is a very powerful result. Let X be a sequence of independent and identically distributed IED random variables defined on our probability space. The crucial condition here is that the expected value of the absolute value of X sub n is finite. The slide mentions the supremum over n of E absolute Xn is less than or equal to B, which holds if they are identically distributed and expectation of absolute x1 is finite. Then if the x sub n are IID and E absolute x1 is finite, which implies Ex1, let's call it mu, is also finite, the empirical n mean Sn over n converges almost surely to mu. The proof of this version of the strong law is more advanced and typically involves techniques like truncation and leveraging strong laws for bounded variables or specific subsequences, often in conjunction with Kronecker's lemma. So we do not go over it in this lecture. These laws of large numbers and the central limit theorem are truly the bedrock of much of probability and statistics, explaining why averages tend to stabilize and why normal distributions are so ubiquitous. This concludes our lecture on weak convergence and the strong laws.